All right, gang, Mass 6610. Again, apologies for the abrupt ending. It actually turned out to be a blessing because I want to keep my video somewhere around 20 minutes, and I think it was about 25 minutes. Technical glitch. Actually, I had technical glitches throughout the video, which explained a little bit of the reason I was so distracted. But hey, we got through it, and here we are. So, moving into effect sizes for Ancova, and for uh, Ancova effect sizes, we use again partial eta squared recall. So think the 0.01, 0.06, 0.14 are the thresholds or cutoffs for the small, medium, and large effects, respectively. The calculation for the partial eta squared is very, very simple. It's just the sum of squares for the effect divided by the sum of squares for the effect plus the sum of squares for the error. Now, we'll need to calculate an effect size for the group and the covariate. And to calculate the sum of squares, I want you to use the type 1 sum of squares method that we've discussed previously. So let's create our Ancova design, our Ancova model. Now you'll see that I've already converted the group term over to factor, and it's going to be called F group. So I want to run my ANOVA on final exam for F group plus the covariate ACT. So we'll just do summary and COVA, and we get our output. So the partial eta squared for the covariate here will be the sum of squares for the covariate, which is 8538 divided by 8538 plus 4027. So we have a large effect size for the covariate, partial eta squared for, let's just call it, yeah, whatever, group is 160 divided by 160 plus 4027. So the partial eta squared for group is 0.038. Yeah, so we're somewhere between a small and medium effect size. Um, Now, well, I'll tell you what, I keep wanting to tell you what's going on here, but I want to actually do that, explain all that in the last video, and then I'll show you how we write it up and present the results and so on. So let's get into G power. So you should be no surprise that the Ancova used the F test, and well, the default is Ancova. We want a priori and to determine the input parameters. I think the easiest way, since we didn't calculate the F effect size, we can come over here and do a direct. And what I want you to put here is the model. So this would be the F group. So I would want you to do 0.038 and then calculate it, shoot it over to the main window. Let's just close this. So I want 0.05, I want 0.80 here. Degrees of freedom from the numerator. Well, if we come over, we have 2 degrees of freedom. We have 3 groups. And we have a number of covariates is equal to 1. All right. So we're quite short on adequate sample size. I think I don't recall, but I think we had 51 subjects here. Yeah. So to get a power of zero point 0.8, we need about 247 subjects. Now we may want to come in and see what kind of power that we are getting, so we can analyze the post hoc here. Effect size will be the same. Total sample size is 51. Numerator degrees of freedom, groups and covariates. So calculate. And we're getting a power of 0.22. So if the null hypothesis is false, which again, I'll get into the hypotheses in the next video, what we're actually testing here. Slightly different approach than I'm used to, but there's a reason for that. Then we have a 0.22 probability of rejecting a false null. So that's really about all I want you to know in this video. I feel like I'm forgetting something, but well, I would say, just as kind of a parting thought, since we have low power, it may explain, definitely has contributed to why there wasn't a difference in the group. And let me explain why this. So if I look at T apply, I remember that if I look at the final exam score over F group and look at the mean, you'll notice that there's quite a bit of difference. The students who I taught using R scored quite a bit higher, about 3.5 points or so than those using StatCrunch, and about 4 points higher than the one using the graphing calculator. So it was surprising to me that um, the instructional design, or I'm sorry, the instructional delivery didn't turn out to be statistically significant. And ladies and gentlemen, that's probably right here what explains it. So, all right, gang, all I got. Take care.